This is the continuation of EE5508 optical processes in semiconductors. In the last session, we discussed exciton. Let us recap the concept of exciton. Exciton is due to the attraction of free electron in the conduction band and free hole in the valence band by Coulomb attraction. This is different from the donor and acceptor pair. Donor-acceptor pair is based on the crystal structure and the distance between the donor and the acceptor. For exciton, this is due to the Coulomb attraction between the free electron in the conduction band and free hole in the valence band. And it can be obtained through Schrödinger equation. So we have to view the free exciton in the semiconductors is due to the Coulomb attraction. And the distance separated between the electron and hole are over many unit cell or over many lattice constant. Although there's Coulomb attraction between the electron and hole, and therefore it will give rise to some binding energy, the Coulomb attraction is weak compared to a hydrogen atom between the proton and the electron. Now, there's another type of exciton known as the Frecker exciton, where the electron and hole separation is just of a lattice constant apart. So the Coulomb attraction is very strong, and therefore the binding energy is very large. It's because the exciton is derived by Wiener-Mott used by solving the Schrödinger equation, so it's called the Wiener-Mott exciton. So in semiconductor, Wiener-Mott exciton is also known as the free exciton. Now, we have to view electron and hole as one particle. So there are some kind of binding energy that bind them together. And we shall see what is this binding energy when we solve the Schrödinger equation. But conceptually, we have to understand that in order for the electron and hole to be bind together, there should not be any disturbance by the temperature, because temperature itself provides the thermal energy. And exciton travel inside the crystal, just like individual electron or hole. And it will be interacting with the lattice or get scattered with the lattice. And lattice are basically atomic vibration. And there will have thermal energy. And this thermal energy is phonon energy. So the exciton basically traveling inside the semiconductors will collide with the phonon. And this collision of the phonon basically will dissociate or break up the exciton into individual electron and individual hole. So they are no longer an exciton. So as long as the thermal energy is greater than the binding energy of the exciton will break up into individual particle, which is electron and hole. So in order to hold the electron together to form exciton, the binding energy must be at least greater or equals to the kT, which is a thermal energy. So at room temperature, gallium arsenide, the binding energy is 5 MeV that bind the electron and hole together. But the thermal energy is 25.9 MeV. Therefore, the thermal energy is greater than the binding energy, and therefore, all the exciton in gallium arsenide will be dissociated into a free electron and free hole. So you do not expect to see exciton in gallium arsenide at room temperature. However, you will still able to see gallium arsenide at low temperature because the thermal energy at low temperature will be reduced. So in solving the Schrödinger equation, there are two parts. One is the center of mass coordinate and one is the relative coordinate. So as I mentioned, you have two masses, okay? So by classical mechanics, you have a center of mass and a center coordinate. So you take this as origin. So this total mass will be ME plus MH. The center of mass coordinate will be written in this form in classical mechanics. The relative coordinate, okay, basically is this R. So if this is x1, x2, or we call it R1 or R2, then R1 minus R2 is the R, which is the relative coordinate. And for relative coordinate, you have to use reduced mass, which is defined in this way. So in solving the Schrodinger equation, you have solved two parts. One is the center of mass motion, one is the relative coordinate motion. So E to the subscript R, big R, is the total energy, is the energy in the center of mass motion, and E to the subscript small r is the relative coordinate energy. So in solving the Schrodinger equation, the center of mass motion, okay, the wave function can be easily formed to be EIKC dot R. Kc is the wave vector, okay, for the center of mass motion. And the energy is given as h bar squared Kc over 2 big M star. When solving the relative motion, okay, you're basically solving the kinetic energy plus the Coulomb attraction. And this is none other than solving the hydrogen atom for electron and proton. So I will just quote the result, and this can be found from a standard textbook, where the energy, okay, due to relative motion will be equals to this form. The first part, okay, mr star over m naught times RH over epsilon r is basically the binding energy of the exciton. And of course, exciton will have many different levels, n equals to 1, n equals to 2, n equals to 3. Just like in hydrogen atom, you will have a series of excitation line. And n equals to 1 will give you the exciton binding energy, which is written in this form. And this is easy to calculate because mr is just a reduced mass of the semiconductor. RH is 13.6, which is the Ribot energy, and then epsilon r is the relative dielectric constant of the semiconductors. Now, in hydrogen atom, the lowest orbit where the electron, okay, moving around the proton is known as the Bohr radius, which is AH. And this is calculated to be 0.0529 nanometer. Similarly, for exciton, you also have Bohr radius. Okay, so the radius of the exciton is basically the Bohr radius times n squared. If n equals to 1, okay, the smaller radius of the exciton will be equals to AB, which is the Bohr radius of the exciton. So the Bohr radius, okay, can be expressed in this form. I will just quote the result. Okay, it will be given to you in the exam as a reference, as a formula, and you can just basically use the result to calculate the Bohr exciton. M naught, free mass, epsilon r, relative dielectric constant of the semiconductor. AH is the Bohr radius of the hydrogen atom. Mr is the reduced mass. So when n equals to 1, the free exciton has the largest binding energy. Okay, so down here n equals to 1. Okay, that is your binding energy. And when n equals to 1, the radius of the exciton will be equal to AB, which is the smallest radius, and we call that the Bohr radius. So similarly, in slide 55, when we talk about donor, basically the electron orbiting around the donor, you also have a Bohr radius. And the smaller radius is called the ball radius. Again, m naught epsilon r times AH expressed in terms of the hydrogen ball radius divided by me star, where me star is the electron mass of the donor, and we take it as to be the same as the electron effective mass of the semiconductors, because we model the shallow impurity inside the semiconductors using the hydrogen model. So using that two formula, we can calculate the ball radius and the binding energy of gallium arsenide. Okay, given the dielectric constant, the electron effective mass, hole effective mass, and the reduced mass. Okay, using equation 2.7.12 and 2.7.14. Now, again, the total energy, we have to look at the total energy of the electron. Okay, go back to the Schrödinger equation. Okay, the energy is ER, center of mass motion, plus E small r, the relative motion. So for the total exciton energy system, you have to include the band gap, which is the minimum of the gap of the energy of the system, plus the energy E small r and E big R, relative motion, and the center of mass motion. The relative motion, okay, is again, we have obtained in this value, okay, the binding energy times 1 over n squared, where n is the quantum number, and E big R, okay, is h bar squared k squared over 2m. Okay, so band gap minus the relative motion energy plus the center of motion energy. That is the total exciton energy. This Kc, okay, is a center of motion, center of mass motion, will be include the wave vector of the electron plus the wave vector of the hole, because exciton is due to the Coulomb attraction between the free electron and free hole. When Kc equals to 0, the magnitude of the wave vector of electron is equal to the wave vector of the hole. And this is often the case in semiconductors. So for the exciton energy, it will be just Eg minus this term, because Kc is 0 down here. So it will be just Eg minus epsilon b 1 over n squared. So when n equals to 1, okay, it will just have the epsilon b, which is the binding energy. So this is called the free exciton transition energy. Now, to represent it in the schematic diagram, we cannot use, okay, the standard energy diagram in the semiconductor to represent exciton. The reason is because exciton consists of two particles, electron and hole. And the standard energy diagram of semiconductor is plotted as energy as a function of k, and this k is actually the wave vector of one of the electron, which is one particle model. So in two particle picture, it should be written in this way. This is the ground state of the exciton, okay, which involve the electron and hole, because the k itself is Ke plus Kh. So at k equals to 0, first you have n equals to 1. Okay, if you run n equals to 1, n equals to 2, n equals to 3 until the continuum. So from the continuum, measure downwards to the ground state, that is your band gap. Minus off the binding energy from n equals to 1 to the continuum, that gives you Ex, which is the free exciton transition energy. Now, next, besides free exciton, we have bound exciton. Impurity can also attract exciton, and they become localized at the defect state. One simple example is electron bound to donor. So if we have donor down here and if we have electron, okay, orbiting around the donor, okay, slightly below the conduction band, okay, this is a plane of the conduction band. So just below this plane, you have donor state. So the electron is basically orbiting around the donor. Now, you have a free hole, let's say, at the valence band. So let us represent this as a plane of the valence band, okay? And the hole basically will attract to the electron of the donor. So as the electron moves around the orbit of the donor, the hole will also track the electron, okay? So it will actually, the hole will move in the electrostatic field of due to the electron and hole of the fixed dipole, okay? So it basically determines the instantaneous position of the electron. So as you move, this hole will track. So there's this attraction between the hole and the electron bound to the donor. So basically, the hole itself will also travel, the electron will travel around this donor and the hole will track, okay, the electron. So this complex kind of attraction, we call that the bound exciton. Without going into details, you also can have electron associated with an acceptor, and that also can be called a bound exciton. So the bound exciton transition energy will be Eg minus Eb minus the binding energy, okay, of the bound exciton. So it's slightly lower than the binding energy of the free exciton. So if you look at the exciton absorption, exciton peaks are very sharp. It's almost of a delta function. So if we plot the absorption coefficient as a function of energy, okay, especially at low temperature, you will see a series of sharp peaks. Okay, for band gap recombination, free electron and free hole recombination, you expect to have a square root dependence, where this is the band gap. For exciton, you expect to have sharp peaks. Okay, so this is a free exciton, n equals to 1, n equals to 2, n equals to 3. Below it, sometimes if you're a donor, you could have a donor bound to the exciton. So the X represent, okay, D0 represent donor bound to X, which is D. We call that the bound exciton. So the absorption coefficient actually is a summation, okay, of this transition energy of a delta function. We expect this to be very sharp peak. However, in reality, you expect to have some kind of broadening, okay, in terms of the spectral line width. Okay, it's not delta function, but it's have a line broadening, or the line width have certain broadening effect. This is because as exciton travel inside the semiconductor, it will collide with the lattice or collide with the impurity. And therefore, this kind of scattering effect will cause the broadening of this exciton peak. Okay, especially at high temperature, the lattice is vibrating, okay, from at this equilibrium position. So at high thermal energy, it will vibrate rigorously. Basically, there will be high phonon energy at high temperature. So as you go to a higher temperature, as I mentioned before, if your binding energy is less than the thermal energy, or the thermal energy is greater than the binding energy, the electron will get dissociated, okay, or break up into free electron and free hole, no longer an exciton peak. So therefore, probably at higher temperature, you only see the band edge, okay, emission, without seeing the exciton peak. This is experimental data of the absorption coefficient as a function of the photon energy measured at different temperature for gallium arsenide. So you can see that at low temperature, let's say 21 Kelvin, this is your acetone peak, very sharp. And then at 90 Kelvin, okay, you also see the acetone peak. 185 Kelvin, you still see the acetone peak. And of course, remember that band gap changes with temperature. So as you increase the temperature, the band gap will reduce. So the peak is shifted to a lower energy. At room temperature, you no longer see the peak because at room temperature, the thermal energy, okay, is greater than the binding energy of the acetone. So the acetone is dissociated, okay, or break up into a free electron and free hole, but they do not have Coulomb attraction. So let us calculate at 185 Kelvin, what is kT? So Boltzmann constant times the temperature is about 16 MeV. Okay, and we still see a strong acetone peak, even though the kT itself is 3 times greater than the binding energy. Remember, we calculate the binding energy of the gallium arsenide to be about 4.7 MeV or about 5 MeV, okay, at room temperature. So in principle, at 185 Kelvin, okay, we expect we should not be able to see the acetone peak. Okay, so basically the criteria that we use that for binding energy to be greater than kT for the acetone to be dissociated is too stringent. However, for analytical analysis, we will take this comparison on the binding energy of the acetone to compare with the thermal energy. Sometimes experimentally, you may see a slight deviation from this criteria. Now, acetone persists at room temperature. For example, gallium nitride. At room temperature, you still see a sharp peak down here. That is due to the acetone peak, measured at 300 Kelvin. That means the acetone still persists at room temperature. For gallium arsenide at room temperature, the acetone basically disappeared. It's just a band edge absorption. For gallium nitride, you are still able to see the acetone peak. Now, acetone peak, because the peak is sharp and narrow, it has been used basically in optical communication. Now, let us talk about acetone recombination. So again, the two particle diagram, this is the continuum state where n tends to infinity. This is the measure from the ground state. There is the band gap. This is the binding energy of free acetone. This is the binding energy of the bound acetone. Let's say in a photoluminescent experiment, you expect at low temperature, you're able to see Coulomb attraction between the free electron and free hole, and therefore you're able to see acetone. Now, let us look at the next experiment of a photoluminescence of gallium arsenide at 2 Kelvin, measured at very low temperature. So this is the photoluminescence intensity. This is the measured as a function of photon energy. So you see a few peaks down here. This part is due to the free acetone peak. And this semiconductor have donor, so you also expect to see donor bound acetone peak. D0 neutral donor, X stands for the acetone. So this is the bound acetone peak. Now, if we blow up this part, in this diagram, the inset, you can see a series of sharp peaks. These are free acetone peak due to n equals to 1, n equals to 2, n equals to 3, n equals to 4. Now, this sample is different from B and C. B and C are of the same sample, but the sample is basically heated with a high intensity. Now, remember that if your intensity is too high from the laser beam, it will induce heating. So heating is basically thermal energy, and therefore you may not able to see exciton peak anymore because the thermal energy could be greater than the binding energy, and therefore it dissociates the electron and the hole. Another example, if you have performed a photoluminescent experiment of gallium arsenide at 10 Kelvin, low temperature, you see two peaks, exciton peak and bound exciton peak, something like this. Okay, free exciton peak and a bound exciton peak. Assuming the exciton peak that you see, okay, is n equals to 1, you take as n equals to 1, observe at this energy. Find the binding energy of the free exciton and the bound exciton. The band gap of the gallium nitride is given to you at 10 Kelvin. Electron and hole effective mass also given to you. Dielectric constant is also given to you. 8.0 is the relative dielectric constant. So dielectric constant is the relative dielectric constant times the permittivity in free space. So if you go by the two particle picture, okay, this is measured from the continuum to the ground state. So this is the band gap energy. From here to here, this is the binding energy of free exciton. And measure downwards, this is the binding energy of the bound exciton. So from this level, you measure the ground state. This is a free exciton transition energy. From this level, you measure downward is a free or is the bound exciton transition energy. So the free exciton binding energy is basically, you can just take the band gap minus the free exciton transition energy, you will get the binding energy, which is 20 MeV. If you take the free exciton transition energy minus the bound exciton transition energy, you will get the binding energy of the bound exciton with about 8 MeV. Now, if you were to go by calculating using the formula for the binding energy of the exciton, which is of this formula, as we have discussed before. So the reduced mass can be calculated since electron and hole effective mass are given. RH is 13.6, epsilon r is 8, and n, let's say we take equals to 1, we get about 26.8 MeV, not too far off from the experimental result of the free exciton binding energy. Now, remember that when we calculate the exciton binding energy, we solve the Schrodinger equation, okay, by using the hydrogenic model. So you may expect a slight deviation, okay, of the binding energy, okay, from the experimental result. For analytical calculation, okay, for this course, we can calculate using this formula for the binding energy of the exciton. To summarize chapter 2, okay, we have discussed absorption, reflection, and transmission coefficient in semiconductors. For absorption, we talk about direct transition in direct bandgap semiconductors, and indirect transition between indirect valley. Basically, we need two-step process, and this involves the absorption of phonon and emission of phonon. Absorption bound to carrier by carrier bound to shallow donors and acceptor. That is the transition between the shallow donor and the conduction band, and also the transition between the acceptor and the valence band. From this absorption, you also can calculate what is the ionization energy of the donor and of the donor and the acceptor, okay, by measuring the optical absorption instead of measuring the transport property. For high doping effect in semiconductors, we talk about mode transition, band tailing, Bernstein mode shift, and band gap narrowing. Okay, and then we also talk about radiative transition, talking about the carrier lifetime, carrier minority lifetime, and the radiative efficiency. In optical transition, we talk about band-to-band transition. Okay, we talk about free-to-bound transition and donor-acceptor pair transition, and we talk also about optical band trap transition. And we also mentioned that the band gap depends on the temperature. The lower the temperature, the higher the band gap energy. And then we talk about exciton in semiconductor, which is an important concept because due to the Coulomb attraction between the free electron and the free hole. So in semiconductor, okay, the exciton formula was derived by William Mott, these two scientists, so it's called the William Mott exciton. Otherwise, we can easily call it a free exciton. If it's a free electron and free hole, okay, bind together through Coulomb attraction, okay, and I mentioned it's different from the donor and acceptor because these are depend on the crystal structure and also depend on the distance between the donor and the acceptor, even though there is a Coulomb attraction between the donor and the acceptor. Fractal exciton, okay, we did not discuss much because it occurs only in molecular crystal. And we solve Schrödinger equation to obtain the exciton binding energy, the transition energy. And we also talk about the exciton. Basically, the exciton can be bound to impurity. So for example, you have a shallow impurity, the free hole can be bound to the donor impurity. And then we will talk about the exciton adsorption as well as the exciton recombination. This ends chapter 2.